Teams in 6141, Robotics, Science, and Systems, implemented control, perception, and planning algorithms on the race car robot in order to complete two main objectives. Our first objective was to circumnavigate the MIT tunnel system underneath the status center while avoiding cones. Our second objective was to parallel park the robot between boxes from a random starting point. It then leaves the parking space to exit the map. Both of the challenges relied on the coupled functionality of path planning and trajectory tracking. The Path Planner is an optimized version of the Rapidly Exploring Random Tree Planning Algorithm, or RRT.
We use Dubin's curves to create curves which can be physically driven by the car. We then implemented RRT to use those curves to randomly look for paths to the goal. It can generate paths that go forwards, or ones that go forwards and backwards. These are the trees generated by RRT. Our trajectory tracker can drive paths that reverse directions and self-intersect. In order to swerve around cones, we create fake walls shown in white and then plan around them using RRT.
This is what the robot sees while driving. The color threshold filters out anything that isn't an orange or green cone. A bounding box is drawn around the remaining parts of the image that also meet cone area and aspect ratio criteria. When the robot perceives a cone, it plans an avoidance path by sampling points to one side and iterating through possible trajectories. It then chooses the best path, as seen in blue, to correctly drive around the cone. During the RSS challenge, our robot successfully navigated the tunnels and correctly drove around all cones. The course was completed at a slow pace because real-time path planning required additional computation time. Initially, the robot would plan multiple loops around each cone. This was resolved by ignoring cones seen close together. For the parking challenge, the race car managed to successfully park, unpark, and exit the lot from almost any starting location on the map. Occasionally, the car was unable to complete the planned path when it lost localization. This problem was mitigated by adding more features to the map.
Our implementation was interesting because it combined physical robot dynamics and planning computation. Specifically for the RSS challenge, the main issue was speed. Our maximum speed was based on how long the robot needed to replan the path, which highlighted the design trade-off between efficiency and robustness. The parking challenge focused on planning, but a major takeaway came from troubleshooting localization. It made the team realize how important each building block of an autonomous system is. When localization broke down, even a well-implemented planner and path follower failed to perform adequately.
During the final runs, our 6141 team had very successful demonstrations. It was amazing to see the culmination of our strategic implementations of planning, perception, and control. We hope to extend this knowledge in the future by working towards solving even more complex robotics challenges.